Happy Monday, part 2. Any questions about anything? Comments? Comments are welcome too. Yeah. About assignments 1, 2, or 3. I've answered every single question on Earth. There are no questions left. But if there are any questions or comments at any time, feel free to interrupt. I consider the people here now to be smarter than the average, because you know that FlowViz is going to be on the exam. Also, I think it's really, really great to attend lectures. I think it's a mistake to miss lectures and just say, I will catch up later. Because that's 1 hour less that you're thinking about the material. You know, that's 1 fewer hour. And for a lot of concepts, you need more than 1 time to understand them. You see them 1 time, you don't understand it, and you need a 2nd time. And now you get the 1st time out of the way, so to speak, before the exam. So I think it's very wise. Okay, so we're going to continue on with FlowViz. And some of the material will be non-trivial today in this particular hour. I hope that everybody can follow along, and if not, please just raise your hand and interrupt and tell me that I wasn't clear about something. So we're going to look at some new topics, direct flow visualization with arrow glyphs, and then we're going to look at numerical integration techniques for flow visualization. So this is non-trivial because it gets into some mathematics, and I know that a lot of people don't like mathematics at Swansea University. So it will be one of the more mathematical topics that we study, well, because it's a mathematical operator, so that makes sense. And then after that, we won't have time to cover all these topics today. Probably we'll stop, halfway in between, and then continue next Monday on streamline placement, I think. I'm not 100% sure, but that's what my experience tells me. So we mentioned this term direct flow visualization earlier today. We're going to continue on this topic, direct flow visualization using arrows or glyphs. So on the right, we see a vector field. And for every data sample, there is an arrow glyph attached to the data sample indicating the direction of the vector. That's called direct flow visualization, right? There's no interpolation necessarily going on there. All the arrows are the same length. So the magnitude information has been taken away. You can't tell like where the fast flow is or where the slow flow is, so to speak. In 2 dimensions, this is a 2-dimensional steady-state flow. It's a useful technique. And in 3D, it gets to be more trivial. And this is a little bit difficult to understand in a cognitive sense, and it's very frequently used. Anybody know why this is a little bit difficult to understand just by looking at it? Anybody have some ideas on that? It's because what you're doing when you look at that image is you're trying to figure out the pattern in there. You're looking at it going, oh, what is the pattern? Actually, what you're trying to do is you're trying to imagine dropping a massless particle into the flow and watching where it goes. That's what you're trying to do. Everybody sign the attendance? Like, where does the flow go? You're trying to work that out in your mind with this picture. In other words, another way of saying that is you're trying to join up the arrows to create paths. That's really what you're trying to do when you see that image. You want to start joining up the arrows, like connect the dots. That's what you're trying to do in your mind. I can tell because I'm a mind reader. And that's what makes it difficult to understand. That joining of the arrows or trying to trace paths of flow, that's also called integration of the flow. So you're going to hear that term many, many times. Trying to trace the path of a massless particle when it's dropped through the flow, and that's one of the major topics of today. This is used quite a lot, right? Especially if you watch the weather report, you'll see glyphs being used. Here are some examples. So this is glyphs over our favorite islands. Right, and you can sort of see some things going on, right? Black and white arrows. They're not very high quality images, so it's not that easy to see what's going on. Here are arrows with some color coding added. So here we can see like low velocity areas, and here we see high velocity areas, and so on. We can apply glyphs in 3 dimensions. That was a 2-dimensional example, by the way. But look at what happens in 3D. There's a 3D glyph here, and there's the exact same 3D glyph here. But you cannot tell just by looking at these two if it's been projected forwards, down, or it's facing this way. The orientation is ambiguous if it's facing us or pointing away from us. That's due to perspective shortening. That's the shortening of the arrow that occurs when you project it from 3D to 2D. That's called perspective shortening. So it can help to add lighting and shading to the arrows, and of course it will help if we can rotate the 3D scene. That will make sure that that's no longer ambiguous. Here are some arrows in 3D. These arrows are all confined to a slice in 3D, right? So they show the direction of the flow, but they're not, and they don't cover the entire volume. A slice has been taken through the 3D volume, and then arrows have been attached to the slice. Same here, these are 3 slices through the flow, and then arrows are attached to the slices, and we can get an image of the flow. Again, we're trying to do the same mental integration in 3D as we did in 2D. We're looking at that image and we're like the gears of our brains are turning, trying to actually trace paths of movement when we look at those images. So there's something like, it's almost like a stress to look at them. Yeah, because our brains are trying to understand the motion that's conveyed by those arrows. This is an example of some terrain and then flow vector field arrows combined on the terrain that show, for example, the direction of wind. Okay, so that's a little bit about glyphs, using glyphs and arrows attached to vector fields and vector field samples, and I saw some people already doing that as part of their kind of assignment 2 preparation, that you can do that as part of assignment 2, although it doesn't fulfill the complete requirements of assignment 2, but it is an option. Now we're going to talk about streamlines. But before we talk about streamlines, do I have any images of, let me just make sure. I'll show a preview first. Why don't we show a preview? What is this one? Here's a kind of preview of what we're about to talk about. It's called Streamline integration or numerical integration to compute streamlines. Anybody know what a streamline is? A streamline is a curve that's everywhere tangent to the vector flow or the vector field. It's the path a massless particle takes if you drop it into the flow. Anybody know what the word tangent means? We sort of already discussed that. That's something that everybody here, I'm sure, knows. Tangent. How about Nicholas? Nicholas, what do you think tangent means? Sounds familiar, doesn't it?
It does, yes. I can picture it in my head, but I can't put it into words.
I see.
It's like a direction or something, a line like off the. I can't put it into words. Sorry.
Can anybody help out Nicholas, or are you just going to watch him struggle? How about Shugo? Shugo here. Shu, any idea what tangent means? Perpendicular. So it's exactly the opposite. It's exactly the opposite of perpendicular. It means aligned with. Aligned. Yes. Perpendicular means orthogonal, so at a 90-degree angle. Tangent means aligned with. So we're talking about computing curves that are aligned with the vector field. They line up with it. And this is what the process looks like. That is the process. This is a numerical integration process. It is computing streamlines in a 2D vector field. That's what that animation was showing. And the question is, how do you do that? How is that possible? How can we compute streamlines? And in order to do that, we need something called a streamline integrator. And that is what this, it's also called numerical integration. Has anybody here ever taken calculus? You're shaking your hand a little bit. So you almost took it, or you were in the room when it happened, but like you were asleep at the same time, or?
I did A-level maths, which includes most of that.
Okay, good, good. You don't have to know calculus to do well on the exam, but numerical integration does stem from calculus. And this is just a little background information. Flow data is also called derivative data. That's a term from calculus. But we also did encounter this very briefly already in the module. We didn't call it derivatives. We called it something else. That's an advanced question. If you can answer that question, you're really on top of things.
Is it a gradient?
Oh, yes. What's your name?
Ed.
Ed, you're awesome, Ed. You're going to do well on the exam. Yes, gradients are derivatives. If anybody can recall, we're looking at the mathematical definition of derivative, of gradient rather. That's what that the first number of points are on this slide. So velocity is considered a derivative dx over dt. So the displacement in x, the displacement of position over a certain unit of time, dt. So displacement in space over displacement in time. That's how you can think of dx over dt. And the solution to we can solve this equation for x to solve the position. That's what the numerical integration does. It solves for the position of x. And the opposite of a derivative is integration, so to speak, or it's a way to solve for x. And that's where this term streamline integration over time comes from. We can call it a trajectory, a solution, or a curve. And this is what the solution looks like in calculus. That's what an integral in calculus looks like. This is the streamline point. So it starts with the initial position, then we integrate the vector field over time. And that is what we would do if we were in a mathematics class. We would learn the different integration techniques and integration formulas and integration strategies. Anybody ever take a calculus class that did that? I remember learning this like for many, many, many hours. But then you discover that in reality, it's not possible. You cannot apply this directly to a real problem in the real world. You have to approximate the solution using something, well, this is really getting off on a side tangent, but a Taylor series expansion. And in this specific case, the Taylor series expansion approximation is called numerical integration. So it's a mathematical solution to the integral, but it's an approximation. That's the theory. So we're approximating this integral. That's the calculus. We don't do that in computer science. You do that if you're in the mathematics department and you study mathematics. What we do is we solve actual problems and we compute with actual numbers and actual data. So we approximate the solution to this integral using numerical integration, it's called. And what we study, does anybody know the branch of mathematics that computer scientists study?
Discrete maths.
Discrete mathematics, exactly. That's what we study. So numerical integrators belong to the class of mathematics called discrete mathematics. And you can think of the calculus as belonging to some other class of mathematics, the continuous mathematics, or there's another way to formulate that, but analytical. So what we're going to look at is the mathematical formula to compute streamlines. That's what we're about to see. In the first approximation, or the first way we're going to do that, is look at something called Euler integration. And this is very intuitive. The slides that we're about to see do not make it look very intuitive, but it is very intuitive. If you had to just imagine how to do this, you would imagine something that is very close to what you're about to see. So the idea is to follow the current flow vector from the current streamline point for a very small unit of time, and therefore distance, and trace out a curve. That's the way it is. And this is what the formula looks like. To compute the next point on a streamline, we start with the previous point on a streamline. For example, the seed. The seed would be the starting point. And we add to it the current vector there and multiply it by a very small amount of time, dt. And we get the next point. So that's the formula, and we're going to go through an example now of applying that formula. And this is very similar to Sally. So Sally keeps coming up over and over in the lectures. Very helpful person, helpful phenomena. Sally is an analytical data set, and this slide is showing us an analytical data set as well. It's a data set that can be derived by some formulas. So to find out the x component of any velocity vector in this example, we just look at the y position, the y coordinate, and multiply it by -1. So for example, if we take this point here, which is, it's 2 units over and 0 units up and down, the x component of this vector is y, the y coordinate, which at this point is 0. 0 multiplied by -1 is 0. So Vx at that point is 0. There's no x component of the velocity at that point. And that's going to be true about basically all the points along that have, 0 along the y. And if I look at the y component of the velocity vector at this point, the y component is the x component, in this case it's 2, divided by 2. So 2 divided by 2 is 1. So the y component is 1. So this x component is 0, there's no x component, and the y component is 1, which means it's pointing straight up. So that's what the vector looks like at that point. That's called an analytical vector field. And we can do this exercise at any point in the 2D space and derive the vectors there. For example, let's do another example right here. So if we want the x component, it's y. In this case, y is what? Who wants to answer that? The y coordinate at that point? Floyd? Is Floyd here? Yep. Do you know what the y coordinate at that point is?
I unfortunately was not looking.
I see. So this point here, right here,
Right.
what is the y coordinate at that point? 1, correct, yes. So 1 multiplied by -1 is?
-1.
-1, exactly. So the x component of the velocity at this point is -1. Everybody follow that? And now what about the y component? That's x. What's the x coordinate of this point here? 0, exactly. 0 divided by 2 is 0. So we have -1, 0 as the velocity at that point. So that's pointing in that direction. Everybody see how that works? So you can pick any point and then you can derive the velocity vector at that point. That's an analytical data set. That's what we're looking at right now. And the formula in this case is this. This is just one formula, one analytical data set. You can choose lots of different formulas. It's just one example. Anybody know what this actually looks like? This vector field? Because remember, in our heads, we're trying to actually imagine what it would look like if we connected all the arrows up and made smooth curves. Name?
Tulsi.
Tulsi?
Yeah. Is it just like a circular pattern that goes outwards?
That's correct. It's circles, not perfect circles though, ellipses, like, you know, a little bit stretched along X, a little bit, or you could say a little bit compressed along Y. So there is the answer. The true solution are ellipses. So actually, if we started here, we would trace out an ellipse that looked like this. But when we look at this slide, it's approximating, it's showing examples using arrow glyphs, like what the vectors look like using arrow glyphs. So that's the part one, we have to understand that. Now, if we choose a seed point, every streamline has a seed point. That means a starting point. How do we compute the second point on the streamline if we are given a seed point or a starting point? And that's what we're going to look at right now. This is the seed point right here. So we're choosing 0, x, and -1, y. Given that seed point, we have to evaluate the vector there. That's the next step. So the vector at this point is 1, 0. So it's I've added the formula here again. So it's for Vx it's -1 times y. Here it is y is -1, so -1 times -1 is 1. And that's where this x component of the velocity comes from, the 1. And then the y component of the velocity is x over 2. X in this case is 0. So 0 over 2 is 0. And that's where what this 0 is. The current flow vector at S0 is 1, 0. We just derived that. And there's the seed point, and there's the current flow vector. It's pointing that way. 1, 0. Everybody see that? Now we're going to choose an arbitrary unit of time. In the Euler integrator example, dt. dt is a unit of time. Right? If you multiply velocity times time, you get distance. We're choosing an arbitrary unit of time called dt, called a half. to input into our Euler integrator. So we don't have to solve for dt in any way. We can just take a value and plug it in there. It's a constant value typically. Now to get the next point on the line, we take the initial point, that's S naught. This is the next point, by the way, the second point along the streamline. We take the initial point, then we add to it the vector at that point, and we multiply it by dt. So the vector field, the vector at that point was 1, 0. And if we do that, if we multiply 1, 0 by dt, in the previous slide it was 1/2. dt is a half. We get 1/2 minus 1, which is the next point along the streamline. So that's the way it goes. So it's just taking that initial point. The initial seed point was down here. The velocity is pointing straight this way, and we multiplied it by 1/2. That's all we did. We pushed it a 1/2 unit in that direction. And our next seed point is a 1/2 minus 1. Everybody, hopefully that makes sense. I think that's the part that's a little bit difficult to understand. But it's very intuitive, actually. It's really intuitive. If I said, please come up with a way to compute the next point on a streamline as a homework assignment, I think you'd all come up with something similar to this. And then the process just recurses, or it does the exact same thing over and over again. There's nothing different about any of the future steps. It's the same process over and over and over again. Take your previous point, evaluate the vector at that point, and multiply. So it's the same thing over and over again. So the vector at this point, at the next point, is 1 1/4. So we can use that to compute the next position along the streamline. And that's what it looks like. So the next point along the streamline is the previous point multiplied by the velocity at that previous point times 1/2. dt is a 1/2. And we get 1 in minus 7/8 for y. The vector at point S2 is 7/8 over a 1/2. And we just plug it into the formula again. And we get the next point on the streamline. So it's the same formula over and over again. The numbers are getting more complicated as we go along because we're not on exact lines. And this is the streamline, by the way, down here with the 4 points. And we keep going. The numbers get more complicated. Right, here's 9 points into the streamline, the 9th point. There's the 14th point. And there is the 19th point along the streamline. So it's just tracing a curve in the vector field along the streamline. Now, the end of the streamline, so to speak, this is an arbitrary end, by the way. We haven't talked about like when to actually stop the computation yet. In this example, we just stopped the computation after 19 steps. If we know the solution is actually supposed to look like an ellipse, a closed ellipse, a closed loop, then we can see that this is not a closed loop, and therefore there's some error being introduced. Numerical integration is an approximate solution to the analytical solution. And there are different ways to approximate analytical solutions. This is one of them. And we can make it more accurate by shortening the space between points. We chose a dt of 1/2, but it was just it's a starting point. It's just, you know, it's an initial guess. If we close this gap a little bit, we can make it more accurate. So this is change the result. If we change dt, instead of 1/2, we use 1/4. And then we compute the streamline again. See how the points got closer together, the streamline points? The distances between streamline points got shorter. And then this got closer to approximating an ellipse. This is using 36 steps. And this is some results that compare different DTs, or the space between the steps along the streamline. So we started out with 1/2, dt 1/2, and that is this one here, this streamline on the outside. If we shorten it to 1/4, we get a streamline that looks like this. If we shorten it to 1/10, it's this orange streamline. If we shorten it to 1/100th, it's the green one. So the green one is the most accurate, right? Where the dt is the smallest. Can anybody think of any advantages or disadvantages? If we decrease dt and make it more accurate, is there any disadvantage to that? Luke?
It takes longer to compute.
Exactly. So we're always trading off accuracy and time, computation time. That's the idea. So, did I lose everybody? Any questions about that? The good news is, if I did lose you, you can rewind it and watch it again in slow motion. Yeah. Okay, so that is the Euler integrator, or a summary of the Euler integrator. This is a little bit about error, right? If we choose a dt of 1/2 and we integrate for 19 steps, the error we can approximate is roughly 200%, and then so on. Here we got only a 2% error, and if the error is less than a pixel, then we can't see it anymore. And that's usually acceptable. And here it is an experiment. A dt of 1,000th results in many, many steps. That's a lot of steps. And the error is almost 0. Now, there are different ways to approximate a streamline. The Euler integrator is just one approximation technique. There's another one called a Runga-Kutta integrator. And remember, this is what theory looks like. We're solving this integral. We're taking an initial seed point, and then we're computing the velocity multiplied by the time, and we're adding it to the seed point. We just approximated that with an Euler integrator that looks like this. But we can come up with more accurate integrators if we so choose, and there are a number of more accurate integrators. And it has a different formula. The Euler integrator is, the next point is the previous point adding on the velocity at the previous point multiplied by dt. The next more accurate approximation says the next point is the previous point multiplied by the velocity of the previous point plus the velocity at the previous point times dt over 2 multiplied by dt. What does that mean? So it's kind of like a look ahead vector. So there are two velocity vectors being used in the evaluation of the next point in this case. This is like the Euler velocity vector, but this is not the original Euler velocity vector anymore. It's a half of an Euler step. That's what this division by 2 is. So do a half of an Euler step, evaluate the flow vector there, that's halfway towards the origin, and then use it at the origin. That's the origin, by the way, the SI. So it's using 2 vectors to approximate the next streamline point as opposed to 1. The Euler integrator only uses 1. So here's what it looks like in action. Here's our seed point. That's 0 minus 2. And if we look at our original formula, the vector there is then 2, 0. So that's that brown arrow, the 2, 0. The preview vector is a vector that's halfway along the first Euler vector. So look, there's a vector halfway along the Euler vector, and it's right here. See? That's that one. That's called, in this context, it's called the preview vector. That corresponds to these 2 steps. Do a half of an Euler step, evaluate the flow there. So do a half of an Euler step, evaluate the vector there, or interpolate the vector there. So we have 2 vectors, the original Euler vector, and then another one. We combine those 2 together, or we average the 2 of them, and use that to determine the next point along the streamline. In this case, dt is even bigger. dt is 1. So we add this vector, the Euler vector plus the preview vector together, divide by 2. That's what that 2 is there. And we get this vector, boom. And that's our Runga-Kutta integrator, rather. Everybody see that? And it's more accurate than the Euler integrator. It's just a more accurate approximation of the streamline. So that's what it looks like at the next step. If we're at this step, there's the Euler integrator vector. There's the preview vector. We add them together, divide by 2, and we get the next point along the streamline. And so on. So this is a comparison of the two integrators. This is the original Euler integrator, and look, these are the points we're computing with a dt of 1/8. Here is the Runga-Kutta integrator, the green streamline approximation, and dt is 1, which is a lot bigger than 1/8. And they approximate kind of the same streamline. So in this case, Runga-Kutta 2 is only computing 9 streamline points. And in this case, it's comparable to an Euler integrator using 72 streamline points. So it's more accurate, it's more costly to compute each streamline point, but sometimes it can be even faster than Euler because of its accuracy. And there are more approximation methods. So there's Euler approximation, Runga-Kutta 2, and there's a 4th order Runga-Kutta method. And there are more as well. It's not just 4th order Runga-Kutta. In this case, in Euler, we used 1 vector to approximate the next streamline point. In Runga-Kutta 2, we used 2 vectors to approximate the next point. Here, we're using 4 vectors to approximate the next point along the streamline. The 4 vectors are labeled on this slide A, B, C, and D. And each step looks like this. It follows this formula. Right, so this is the previous point. So the next point is the previous point plus A, which is the original Euler vector, 2 times B, which is the same as the preview vector from Runga-Kutta 2, plus these new aspects using the Runga-Kutta 2 again, and D again. So it's using the Runga-Kutta 2 vector 3 times. And then taking the whole thing and dividing it by 6. And it's even more accurate than the previous 2. And here is a comparison of those different approximation methods. So we have on the outside the original streamline computed using the Euler integrator. dt is a half, 19 steps along the streamline. Then we have Euler integrator again, but dt is smaller. It's only a 4th in this case. That's what that looks like. And it computes 38 streamline points. Runga-Kutta 2, 2nd order Runga-Kutta. Where is that? Oh, I need to find that one. It's green, got green points and a pink. It's hiding. It's hard to see, but it's hiding here. See those green points along the streamline? It's hiding there. It's one of the more accurate streamline integrators. So dt is a half. It's computing 18 points. There's Euler again with the dt of 1/8. That is this one. And then Runga-Kutta 4th order is overlapping with the green one. See the green and the brown overlapping? Those are the 2 Runga-Kutta integrators, the most accurate ones. So in this particular case, they're computing the exact same streamline, basically. So this is the summary of integration. So in the ideal world, we would be able to analytically solve or integrate the streamlines, but we can't do that in reality. So we approximate the analytical solution using discrete mathematics. In this case, it's numerical integration. And there are different ways to approximate the streamlines. Euler is the simplest, most intuitive method, I would say, but it's also the least accurate. We can use Runga-Kutta too to get more accuracy, but with a trade-off in speed. And there are other methods. Now that you've seen that, we can look at the animation one more time, and maybe it makes a little more sense. There's the animation again. Now, in that example we just went through on the slides, we looked at an analytical vector field. That means you can input any coordinate position like x and y, and it gives you back a vector. That's actually kind of unusual. In reality, what usually happens is you're given a set of vectors on a grid, like a 2D Cartesian grid or a 3D Cartesian grid. And if you want the vector at any point in that space, you need to use interpolation. You interpolate using the nearest 4 vectors. And that's what this is showing. This is the current point along the streamline, and it's showing the cell that surrounds that point, and that's a data cell. And at the 4 corners of the data cell are 4 vectors. And you can see the 4 vectors because they have these little edges that are pointing in the direction of the 4 vectors. And the vector field is being interpolated at this point using the nearest 4 vectors surrounding in the cell. That's what this is showing. And it's showing a very smooth integration process. The dt in this case is very small. It's something like a 10th, 10 steps. Anybody know what's happening there in that corner? Any guesses? What's happening in the corner there? Anybody want to guess? How about Jan Plesnik?
That's me. Is it just like a circular flow, and the streamline gets like stuck in a circular motion?
That's right. It's also called a sink. It's a critical point, like all the vectors point down the sink, so to speak. And you can see it. You could see, if you look at that cell, there were 4 vectors all pointing inwards. So that's called a sink. And by the way, this is also showing forward integration and backward integration. So you can start with a seed point, and you can forward integrate downstream, or you can trace the streamline backwards. That's called backward integration. So that's what this part is showing. Forward, there's the seed point, there's the downstream flow, and there's the upstream flow, or backward integration. That's what that's showing. Everybody understand that now? These are the four vectors at the corners of the cell as it traces through the vector field. It's a nice little animation that shows a little bit some properties of the numerical integration process. Any questions about that? I can see see everybody's on the edge of their seats with excitement. Okay, we will stop.